Hello friends, in today's question, a uniform rod of length L and mass M is pivoted at the center. Its two ends are attached to two springs of equal spring constant K. The springs are fixed to rigid supports as shown in figure, and a rod is free to oscillate in the horizontal plane. The rod is gently pushed through a small angle theta in one direction and released. The frequency of oscillation is, so this is our rod, and total length of the rod is given as L. Spring constant of each spring is given as K, and mass of the rod is given as capital M, and it is pivoted at this point. Let us suppose this point is P, and it is given a small push through angle of small theta, so which basically means that this is the initial position of the rod, and now it is given a small push such that it makes an angle of theta with the vertical. So this is angle theta, and this is a point P. Okay. And we have to find out what will be the frequency of oscillation of this rod. So as the both ends of the rod are attached to the spring, so therefore as it is being rotated or pushed by a small angle of theta, the spring will be compressed, or we can say expanded. In one case it will be compressed, and in other case it will be expanded. Okay, so if from here, let me draw the figure first of all. So this is a one spring, and this is the other spring. Okay. Sorry, I made a mistake that in both the cases the spring will be extended, not compressed, or you can say one compressed and one extended. So the spring constant is K, and here is also K, and if we say that the springs are extended by the amount X, here also and here also, so therefore there will be a restoring force which will be acting on both the springs, and that restoring force will be in this direction, and let us call that will be over minus Fx, and here also in this case also it will be Fx, and this restoring force is going to generate a torque around the pivot point P, and which we are going to solve further. So from here we can easily say that it is said that this angle is theta, so total length is L, so we are going to have L by 2 length this one, and similarly we are going to L by 2 length in the other end. So this restoring force is going to introduce a torque, and let us call that torque as a restoring torque. So you can say restoring torque from the spring, So we say when the rod is displaced by a small angle theta, theta from its equilibrium position, which was a simple vertical, from its equilibrium position so both ends of the rod are displaced horizontally, and let the displacement is given as X. Both ends of a rod are displaced horizontally by a displacement, and that displacement is taken as x. So therefore we can write that our x will be equal to L by 2 multiplied by theta, where theta is small angle. And if you say that the restoring force on the rod due to spring is given as F, this is F and this is also F, not Fx. So you can say that restoring force on rod due to spring is F. So therefore we can say, or rather we can write, that F is equal to minus kx. We already found out what is x. This is minus k. We get L by 2 multiplied by theta. So this is the restoring force in terms of your angle theta. And now we have two restoring forces. So because of these two restoring forces, there will be torque that will be introduced into this rod. These restoring forces creates a torque let us suppose that is given as tau around the pivot point P. Around the pivot point P. Therefore, we can say the torque due to each spring let us call this as tau spring, will be equal to force multiplied by the distance between the pivot and the where the force is being applied. So that is equal to F L by 2. So this is a pivot point, the distance is our L by 2, and we have a force that is F. So torque is equal to force into L by 2. So we already know the value of force which we calculated. Force is equal to minus k L by 2 theta is substituted here. We get this as tau spring is equal to L by 2 multiplied by minus k L theta divided by 2. This becomes minus k L square theta divided by 4. Now this is the torque because of one spring. So we have two springs. So total torque will be equal to total torque will be equal to twice multiplied by tau spring, and total torque, let us suppose, is given as tau total, which is equal to 2 multiplied by minus k L square theta upon 4. This goes by 2. So we get tau total is equal to minus k L square theta divided by 2. So we found out that our total torque because of the spring, both spring, is given by minus k L square theta by 2. Now this will be, you can say, related to some rotational motion being introduced into the rod. So we can write the equation for the rotational motion. So you can see equation of rotational motion, and we already know that for rotational motion torque is equal to moment of inertia multiplied by alpha, where alpha is angular acceleration and I is the moment of inertia. We can say I is equal to moment of inertia about pivot point P, and that will be equal to 1/12 ml square, and alpha is our angular acceleration. Alpha is angular acceleration, and that can be written as second derivative of angle theta divided by t square. So substituting all these, you can say torque, moment of inertia, alpha, as well as tau total. So this tau will be our tau total. Let me write it here. Tau will be equal to tau total. So we can substitute all the values. Let me write it once again here. Tau total will be equal to I multiplied by alpha. So moment of inertia is 1/12 ml square, and alpha is double derivative of angle theta, and tau total we calculated, and that comes as minus k L square theta divided by 2 is equal to 1/12 ml square, and we have double derivative of theta. So here L square cancel out with L square, and 2 goes with this 6. So we can rearrange the equation, and this rearrangement gives us that double derivative of theta plus this becomes as 6k theta divided by m is equal to 0. Now this equation is the equation for the SHM. So you can see this equation is the equation of SHM. Therefore, you can say angular frequency which is given as omega we can write the relationship that omega square is equal to 6k divided by m. So from here omega is equal to 6k m, and omega is equal to 2 pi f. So we can write here 2 pi f is equal to square root of 6 m, and we get f as 1.2 pi square root of 6k m. So this is the frequency of our oscillation. This is frequency of oscillation for the rod. And if we check the available option to us, you can say that option number C is the correct option. So you can say option C is correct one. So this completes the question. Thank you.